Okay, I'm going to work another problem from 4.6 because I don't know that there are any where you actually have to find the relative growth rate. So I want to do one of these. So this is number 11 from your book. And I just kind of drew a rough sketch of the graph they gave you. But let's just go through it one question at a time. So the A part asks for what was the deer population in 2010. So I'm just going to look at the graph they gave me. And so in 2010, this is a graph from 2010 to 2014. So at time 0, right there on the graph, I'm looking to see what the deer population is, and that's 20,000. So I'm just getting that from 0 on the x-axis and then going up to where my graph is on the y-axis is at 20,000. Then the B part is the part that I wanted to work so y'all will understand how to find the relative growth rate. It says to find a function that models the deer population t years after 2010. Now remember that this relative growth rate is the growth rate after t years equals our initial population, and then we've got a relative growth rate r times t. So if I'm going to find a function, I'm going to leave it in terms of t because that's what it's asking for. So I'm going to leave n of t, I'm going to leave t in my model. So I need to know what my initial population is, and that's what they gave me. But I also need to know what my relative growth rate is. So I'm going to have to find that first. Now I'm going to use what they've given me in order to find that. So if you look back here at the graph, I know that after 4 years, that my deer population is 31,000. So I'm going to use this in order to find my R, my relative growth. So 31,000 is going to equal my initial population, which was 20,000. And then times E raised to the relative growth rate. That's what I'm trying to find. That's what I don't know. Times T, well, from 2010 into 2014, that's 4 years. So I'm going to let that be my time T. Now, in order to solve this, all I need to do is divide by 20,000. And so I know that E raised to the 4R is going to equal, and I'm just going to go ahead and simplify that a little bit, 31 over 20. Well, if I change this to log form, and I'm going to use the natural log because this is E, I'm going to get the natural log of 31 over 20 is going to equal 4R, which means R is going to equal the natural log of 31 over 20 divided by 4. And when you plug that in your calculator, you're going to see that the relative growth rate is 0.1096. All right, so now going back to my original equation, now that I've found the relative growth rate, I can go back and I go, okay, here's my model in terms of t. My model is going to be n of t equals my initial population, which was 20,000, times E raised to my relative growth rate, which was 1.096, times T. So there's my model in terms of T after T years. And that's what the question was asking for. All right, so now I'm going to keep going here. Part C asks for the projected deer population in 2018. Well, now that I have my model, I can find whatever population I'm looking for because I know that's going to be my initial population times E raised to my relative growth rate, which I found. And then T, what's my T going to be here? Well, I started off in 2010. Now I'm looking for the population in 2018. So my population in years, my time in years is going to be 8. And then you're just going to plug this in your calculator. And you're going to get approximately 48,000. And that's all they ask for. They just ask for an approximation. So your C answer is about 48,000 deer. And then the last part of this question, it says estimate how long it takes the population to reach 100,000. So that 100,000 is going to be the amount at the end. It's going to equal my initial population times E raised to my relative growth rate. And T, in this case, is what I'm looking for. All right, so in order to solve this, this is just an exponential equation. You're going to isolate that first. So the first thing I'm going to do is divide both sides by 20,000. So I get, whoops, I don't know what's happening there. So I get 5 equals E to the 0.1096 times T. Change this to log form, so I've got the natural log of 5 equals 0.1096 times T. So T in this case is going to equal the natural log of 5 divided by 0.1096, or approximately 14.7 years.